Alright, welcome back, guys. We will be starting the last module, Module 4, and this just contains material from Chapter 9 from the book. Okay, and you can see here the title is Composition of Functions. You've actually already done this before, you just didn't know it. So composing one function with another, that just means you're plugging the output of one function into another function. Okay, so you're going to have two functions, and the output of the first function will become the input for the second function. Here's a little example, but I found some others. An example of this would be, what if you wanted to convert the temperature in Fahrenheit to Kelvin? Well, you could do it directly, or you could use two functions to do it. You could first convert the temperature in Fahrenheit to Celsius using one function, and then use another function that takes an input from Celsius and then converts it to Kelvin. Okay, so that's one example. There's some other examples of this method, or this concept. Okay, basically, it's basically a sequence of processing. Okay, so the output at one level becomes the input at another level, and this is actually used in software all the time. So let's look at a few examples here. I did a little search in ChatGPT. A photo filter app. Okay, one function sharpens an image, and I've actually used these in Photoshop. Another adjusts brightness, and another applies color correction. And so applying them in sequence would be function composition. Okay. Another example might be, it says, suppose a bank uses one function that calculates interest over a period of time, and then another function that calculates taxes on earnings. Okay, so you know you have to pay tax on interest, and so a composition, and we'll talk about this here in just a second, G composed of F would represent the taxes on that interest that was earned. Okay, here's an example. Think about like a car or some sort of mechanical system. So how the system behaves is going to be equal to this series of functions, or this composition. Okay, you have input that goes to this, the sensor picks up the input. So think about, your car, when your car is running, it's taking input from those different sensors. Okay, and it may be that input from the sensor will give output that goes into a controller, and then the controller, the output there, actuates something. Okay, causes something to happen. So it's kind of like a sequence of events or a sequence of processes. Let's see. This one I liked. So in machine learning, okay, or AI, these neural networks that maybe you've heard about, these are literally chains of composed functions. Okay, so each layer transforms its input, and then the final output depends on the entire composition. Okay, so basically it goes through these sequences, this sequence of functions, and then finally you get some output. Okay, all right, so those are just a few examples. Alright, so we're going to be looking at it more from a theoretical perspective. Alright, so let's look at the notation that we're going to be using. So the composite function, the way you say this is F composed of G. Okay. So that designates, that is not a multiplication symbol. F composed of G. That denotes composition. Okay, and this is the way it's written, F composed of G of X. Okay, so this composition is still a function of X, and the definition is this. Okay, basically you're taking function g, whatever the output from g is, and that's becoming the input for f, because isn't that what this notation means? This, in parentheses here, this is always the input, and then f does something to that input and gives you an output. Okay, and notice here it says where x is in the domain of g and g of x is in the domain of f. Okay, because what you're doing here is x is going to be plugged into g initially, and then that output gets plugged into f. Okay, so it's kind of like you have a double substitution here. So basically we're going to be plugging one function into another. One way you can look at this is f composed of g of x just means you're going to take, so usually there'll be a value here for x. Okay, so whatever that value is, that, well, let me draw it. That's going to go into g, and then g is going to give you an output, and that output is going to become the input for f. Okay, so when you're doing these compositions, it always goes in this order. G is what we refer to as the inner function, and then f is what we refer to as the outer function. Okay. All right, and you know, we saw some examples in which you may have a composition that consists of many functions, not just two. Okay, but that's all we're going to be looking at today. All right, let's look at example 1. So it'll give us the two functions f and g, and then it'll give us composition, or what we're trying to find. So here f is a quadratic polynomial. You should be familiar with that by now. And then g is a linear polynomial, okay, or a linear function. And so we want to find not f composed of g of -2, but g composed of f of -2. Okay. In other words, what we're going to be doing is plugging -2 into f, and we'll get an output, and that output goes into g. Okay. But guys, because this is a math class, I'm going to utilize the actual definition. So the definition would say that g composed of f of x is equal to g evaluated at f of x. Okay. Well, we know the value of x, it's -2. So using the definition from above, this becomes g of f of -2. In other words, what I need to do is figure out what f of -2 is first. Okay, so that goes back to what I was saying. Plug -2 into f. Okay, so this will become g of, I'm going to plug -2 into f. So f here is this quadratic. So I'll have -2 squared minus 1. And this is going to give me an output, and that output's going to go into g. Alright, well, let's evaluate this. -2 squared is 4, and then 4 minus 1 is 3. Okay, so I will be evaluating g whenever the input is 3. Alright, so g is this linear function right here. Okay, so I'm going to plug 3 in for that x. So that would leave me with 3 plus 3, which is 6. So to answer this, g composed of f whenever x is -2 is equal to 6. Okay? So basically we just ran this initial input through to two functions. Okay, it went into f first. F gave us an output of 3, and that became the input of g. And then g gave us an output of 6. Okay. Alright, well, let's look at another one. Example 2. Even think about our bodies, guys. You know, that's what machine learning is attempting to imitate, is basically our mental processing, essentially. But think about your your human body, we have nerves. Those nerves take input, okay, from the environment, and then that affects us in some way physiologically, and then we act accordingly. Okay, so you kind of have a sequence of processes taking place. Oops. All right, so example 2 here. Very similar problem here, guys. F in this case is a linear polynomial. G is a cubic, that basic cubic polynomial. And we want to find f composed of g whenever x is negative 4. Okay, so again, we're essentially just taking negative 4, we'll plug that into g. Whatever that output is will go into f. Okay, but again, I'm going to show this mathematically. So this means we want to find f of g of negative 4. Okay. So I need to plug negative 4 into g. Well, g is this cubic function. So I will be cubing negative 4. And whatever this output is, that'll become the input for f. Well, negative 4 cubed is negative 4 times negative 4 times negative 4, which is negative 64. So that's what I'll be plugging in to f. And then f is this linear function. So I'll have 2 times negative 64 minus 5. We'll do the multiplication first. 2 times negative 64. I'm going to move myself over here. Will be negative 128 minus 5. And we're going to get negative 133. Okay, so we can restate this and say that f composed of g whenever x is negative 4 is equal to negative 133. Alright, well, let's go to example 3. Same thing here. Okay, f is quadratic, g is a linear polynomial, and we want to find f composed of g of 5. Okay, so this means I'll be finding f of g of 5. So g of 5, well, g is this linear function right here. So if I plug 5 in, I'll have 2 times 5 minus 7. Well, 2 times 5 is 10, minus 7 is going to give me 3. So that's the value at which I'll be evaluating f. So I'm going to plug 3 into f. Well, f is this quadratic, so we'll have 4 times 3 squared minus 3, and then plus 10. Okay, so we'll do our exponents first. 3 squared is 9. 4 times 9 is 36, minus 3 plus 10. And you can probably do this in your head. 36 and 10, that's 46. Take away 3 is going to give us 43. Okay, so f composed of g of 5 is equal to 43. All right. So that's some practice evaluating these compositions of two functions, okay, for specific values of x. All right. Now what we're going to do is look at, well, we're going to do a couple things. We're going to look at, so if we have a composition of two functions, let's say we compose f with g, technically we end up with a new function. And so the question then becomes, well, what is the domain of that new function? Because we can find the domain of the two individual functions, but what's the domain of the composition going to be? Okay, and let's talk about this for a minute. Finding the domain of the composition of two functions. Well, there's really two cases, guys. When both of your functions are polynomials, When f and g are polynomials, the domain of the composition is just going to be all real numbers. So there's not much work to do. Okay? Because think about this. If, let's say we want to find g composed of f, for some value of x. Well, if g is a polynomial, it'll take any value of x. X can be any real number. And then g will give us out some number. And if f is also a polynomial, it'll take any number as well. Okay, so it doesn't matter what value g gives us, it'll be an input for f because they're both polynomial functions. Okay. Now, whenever the two functions are not polynomials, that's sort of the second case. Okay, so we're going to look at the second case here in a minute. First thing we're going to look at is when f and g are both polynomials. Okay, so let's look at example 4. Given that f is a linear polynomial and g is a quadratic polynomial, this says find f composed of g of x and g composed of f of x and the domain of each. And we'll be expressing those domains in interval notation. Well, guys, we can, because of the nature of these two functions, because they're both polynomials, we know the domain is going to be all real numbers, so that's should be an easy one. Okay. However, we need to actually find these compositions, and that's what we're going to spend most of our time on. This example, f composed of g of x, according to that definition, means f of g of x. Okay. Now you'll notice there's not a value in here for x, like we saw previously. So what happens is g of x, whatever that function is, in this case it's the quadratic right here, it becomes the input for f. So we're going to be plugging one function into another. Okay. So what I'm going to do is recopy this, but I'm going to replace g of x with the actual function. 2x squared minus 7x minus 4. Okay. So this is now my input for f. So f is this function right here, x plus 4. So all of this quadratic function will go in place of x. Okay. So I'll keep it in parentheses to show what I'm doing. So that is sitting in place of x plus 4. Okay. So you're just plugging one function into another. Alright, well, I can take it out of parentheses now. And I can simplify this a little bit. Those two constants are going to cancel, and I'm going to end up with 2x squared minus 7x. Okay, so that is what f composed of g of x is. It's this new quadratic function. Now, what's its domain? Well, because they're both polynomials, the domain will be all real numbers. But we want to express this in interval notation. So in interval notation, that means negative infinity to positive infinity, or in other words, basically the entire x-axis, right? All right, now what about g composed of f of x? So now we're going in reverse. Okay. Well, this means g of f of x. So now we'll be plugging f of x into g. So f of x is the linear function, x plus 4. Okay. So that is going to go into the x that is in g right here. Well, there's actually two x's. So when I plug this in, because this is a binomial, I'm going to need to keep it in parentheses. So this will become 2 times x minus 4 squared minus 7 times x minus 4. And then we've got that minus 4 at the end. Okay. Alright, so a little bit more work here to simplify this. First thing we need to do is square this binomial. Okay, so we've done that before. X minus 4 squared means x minus 4 times another x minus 4. So x times x, that's x squared. If you do the outer and the inner, you'll get negative 4x and another negative 4x. And then negative 4 times negative 4 is positive 16. And when we combine these two like terms in the middle, two negative 4's give us a negative 8x plus 16. Okay. Now when I plug this back in, because there's a 2 sitting in front, I need to keep this in parentheses because I'm going to be distributing that 2. I'm just going to recopy the rest of it. Okay. Alright, so now I'll distribute the 2. 2x squared. Right here, 2 times negative 8x will be negative 16x, and 2 times 16 is 32. And I'll distribute the negative 7. Negative 7 times negative 4 is positive 28. Minus 4 at the end. We've got some like terms. End up with 2x squared. Negative 16x minus 7x is negative 23x. And we've got some constants. 32 and 28, that's 60. Take away 4 will be 56, I believe. Okay? And so this is G composed of f of x. And so it's this new quadratic function again. Now what is its domain? Well, same as the last one. Because they're both polynomials, or we're just plugging one polynomial into another, the domain will be all real numbers. Okay? Alright. Let's go ahead and just review a little bit more on interval notation. And we're going to see one last example. I may save this last example for a part 2 video, though. Let's talk about it for a minute, though. Look at these two functions, guys. These are not polynomials. These are rational functions. And so if we were to find f composed of g of x, it will only work for inputs that can both go into G, okay? And then the outputs from G are only going to be valid if they can go into F. Okay, so if any input into G makes G undefined, then it makes this whole composition undefined. And then any outputs of G that make F undefined also makes the composition undefined. Okay? So whenever our functions are rational like this, then we are probably going to have restrictions on the domain. But we'll talk about that here in a minute, part 2 probably. Let's just kind of review. Actually I think I'll wait and review in the part 2. It's just a little review on interval notation, and then we'll tackle example 5. Okay, so I'll see you in a minute.